you have Schrodinger's equation, the equation that was developed by Erwin Schrödinger, and the solution of that equation is determined by using the state of the system, by using this complex wave function, which is composed of the real and imaginary part. But the point is that this mathematical argument, this wave function, is completely predictable. It's purely deterministic in the framework of theory. And the tussle only comes in action once you make the observation. And the tussle goes between all the probabilities that you predict, but once you make the measurement, you come up with just one solution. The rest of the arguments, which were purely deterministic in the framework of quantum mechanics, they all disappear and the system reacts to your observation. So it's the observation, it's a tussle between the observation and what is to be measured. Suppose I talk about an electron. So if I have to calculate, suppose I have a particle in a box. Now this particle has a range of probabilities. So from theoretical point of view, you have this particle at all those frameworks at the same point of time. They exist there. It seems weird, but mathematically, quantum mechanically, it's all deterministic. The problem comes once you try to measure it. So making an act of measurement on the system, which is quantum mechanical in nature, what it does basically is the nature reacts to our observation, and the reaction leads to just one probability out of all the probabilities that existed in that system. So here is the core tussle is between the observation and what you are quantum mechanically predicting. And this is something that we don't understand. So there are many arguments that try to explain this tussle between the observation and the quantum mechanical deterministic approach, but you cannot take any of these things as a complete explanation of that tussle between the observation and whatever probabilities you have in front of you. And there are arguments like that come on, your system is already in those multiple